So we looked at double integrals over a rectangular region and turned out to be not too bad. Now let's look over a non-rectangular region, and this, in my experience, is where double integrals get more difficult for students. So we got to slow down and be careful, and it's really going to hinge upon being careful drawing your region. So here, as an example, I'm integrating double integral this 6xy, and it just says dA, so that could be, we could express that as a dx dy or a dy dx. With the rectangle, didn't seem to make any difference, really, right? If we switched from dx dy to dy dx, all we did was, make the endpoints on the inner integral the endpoints on the outer integral. We just switched those. For a non-rectangular region, we have to slow down and be careful, and you have to draw the picture. The place I see people messing up is they try to do everything in their heads without drawing it, without writing it down. So let's see what our region is. It's a triangular region between, so let's draw this. We got, let's draw it over here. So between x equals 0, y equals 2, and y equals 3x. So this is the triangular region that we're looking for. So that's 2. When y is equal to 2, x has got to be like 2/3, right? And so this is the region over which we're integrating. Not rectangular, so I have to be careful. And now we got choices to make. And when we were doing rectangles, the only thing that was really guiding us if we should go dx dy or dy dx for dA was, is it hard to integrate one or the other? And usually, no, they were straightforward to integrate. Here, I'm integrating 6xy. That's just as easy to integrate, or exactly as easy to integrate with x first and then y as y with x. The shape is symmetric. So I've got some choices here. I'm going to write the thing, so it doesn't make any difference the actual function we're integrating. So I can do dx first and then dy, or I can do dy first and then dx. Now, if I do x first, then these inner ones are x. If I do y first, then these inner ones are y. And then the outer ones here have to be y, and the outer ones on this one has to be x. And these two integrals, they have to give me the same number at the end, right? We're essentially getting the volume with this footprint and this 6xy as the roof. So the answer, the volume of that shape should be the same. The value of that integral, that double integral, should be the same. Now, let's see where our differences lie. When this was a rectangle, I'll do the x one first. When this was a rectangle, what did we put? We put the lowest x and the highest x. And we put them in as a number, but I always now want to think of the inner integrals as always curves. The inner integrals are always curves. Now, we did write them as if they were numbers when it was a rectangle, but I could still think of them as a curve because this is the curve, well, in this case here, this is the curve x equals 0. So by writing 0 here, I'm really writing x equals 0. Now, all the way through the shape, when it was a rectangle, our x's started on a line and ended on a line, so we could just put number and number. Now, it kind of depends on where I am in this shape. Down here, I start at x equals 0 and go to x equals, I don't know, some x value. Depends on the height. Oh, depends on the height. Here, I start at x equals 0 and I go to some different x value. What x value? Depends on the height. I want to write this x value as a function of the height. The height is given by a y equation. So I'm going to need to switch this around. Instead of y is equal to 3x, I'm going to write this as x is equal to y over 3. And now I've got this. It starts on the line on the curve x equals 0, and it ends on the curve x equals y over 3. Yeah, where do I end? It depends on the height. How does it depend on the height? Y over 3. Now I can write this as a curve x equals 0 and a curve y over 3. Yeah, this is a y in here, whereas before we had it with numbers. Not a problem, right? We've dealt with, we know how to deal with this. Now it's just not a number, it's a function, but I'm going to do the same thing with it. Integrate, sub in the top minus sub in the bottom, 4x's. So with a non-rectangular region, these inner integrals become curves. And if this is an x, then this is an x equals some curve, could have y in it. This is an x equals some curve, could have y in it. Let's look at, let's finish this one then. Now I've got this whole, I've incorporated this boundary and I've incorporated this boundary. This boundary is incorporated in this, recognizing that it was a line. The outside, I'm going to pick purple. The outside ones are always numbers. They're y numbers. It'll be the lowest y in the shape and the highest y in the shape. So the outside ones are always numbers. Why couldn't they be formulas? Well, if they were formulas and I subbed in the top and subbed in the bottom, then I wouldn't get a definite number. I would get something with a formula in it, and I want a number. There's a finite volume for this. So now, when I do this integration, I'm going to get a value, and now we can just mechanically go through this integration. But this double integral idea over non-rectangular region, it's the setup that's the most important thing. So mechanically we'll integrate this in a minute, but let's do the other setup. Now for the other setup, these are y equals. Now normally if it was a rectangle, I would go y equals the bottom number and y equals the top number, but I want to think of them as curves now. So let's clear this diagram. I don't want to clear that. So I'm starting again. But this time, we would normally, if it was a rectangle, I'd start with y equals. But now, my starting value, I'm starting on that line with y's. I'm going in the vertical with y's. And I'm always ending on the line y equals 2. But where my starting y value, what my starting y value is, kind of depends on where I am. Here, the starting y value is lower. Here, it's higher. Yeah, the starting y value depends on what the x value is. And I already have that dependence right here. The starting y value, it starts on the line. The starting y value is 3x. So I'm starting on 3x, and I'm starting on the curve y equals 3x, and I'm ending on the curve y equals 2. And then the outers are numbers. They're x's. Lowest x in the shape, highest x in the shape. This should give me the same number. Now, why would I pick one over the other? Sometimes one integration is easier, but right now these are equally straightforward. Let's mechanically bang these out then. So our first choice was we picked Our first choice was we did dx and then dy. Our second choice, we did dy and then dx. When we did dx first, our x's started at x equals 0 and ended at y over 3. So it started at 0 and ended at y over 3. And then our y's, we did, for the outside one, lowest y in the whole shape, highest y in the whole shape. And here's our function then that we can integrate. If we did dy first, then we started at y equals 3x and we ended at y equals 2. Those are curves. And then our outside things were numbers. Lowest x in the whole shape, highest x in the whole shape was what? 2/3. And I'm claiming these are equal. Let's actually evaluate these and make sure that we're doing this correctly. So I'm going to do this inner integration first. And I'm integrating with respect to x. So that's going to be add one of the exponents, so it becomes x squared, divide by what's up top, so that's a cubed. And now our endpoints, we're going to go sub in the top minus sub in the bottom, and our bottom here is y over 3. And those are x's. So let's do that. When we sub in the y over 3, I'm subbing it in for x. So that'll be y squared over 9. Y squared times y is going to be y cubed. Over 9, well, with that 3, we're going to cancel and it's going to become an over 3. So if any of that was, whoa, you went too fast, then you stop it, pause the video, and just plug in the top minus plug in the bottom. Minus plug in the bottom. When I make when I make x equal to 0, it's just minus 0. Now all I have to do is integrate. So we actually subbed in these values, so we're good. And now I just got to integrate this y. That's going to be an add one of the exponent, divide by what's up top. So that's going to be y to the 4th. I want to divide by 4. It's already divided by 3, so that's 12. And we're going from the number 2 to the number 0 to 2. And now it's going to be sub in the top minus sub in the bottom. I'm going to get 16 over 4. And yes, we can simplify 16 over 12 minus 0. But let's just leave that for now. I get an answer. So we did sub in a formula, but it was y's in it. And then we ended up integrating it out. Let's do our other piece here. I'm going to do so we should get the same answer, but now I'm going to integrate with respect to y first. So I'm looking at this inner integral. I'm integrating with respect to y first. So that's going to be an add one to the exponent, divide by what's up top. And we're going from 3x to 2 in this case. There's our integration. Now we're going to sub in the top minus sub in the bottom, and we're subbing those in for y's. So I'm going to sub the 2 in for the y, minus sub the 3x in for the y. So when I sub the 2 in for the y, this will become a 4. The 4 times the 3 will become a 12. Minus when I sub the 3x in for a y. That's going to be 3x squared. That's 9x squared times this other 3x. That's going to be 27x cubed. And now our function only has x's in it. We're going to integrate with respect to x and then sub in the top minus sub in the bottom. So when I integrate 12x, I get 6x squared. When I integrate, that's going to be 27. Add one of the exponents, so it's going to be x to the fourth. So I'm going to go 27 over 4, x to the fourth. And we still have to go sub in the top minus sub in the bottom. So we're going to go from 0 to 2/3. All right. Now, these are x's we're subbing. Well, there's only x's left. So when I sub in the top, I'm going to get 6 2/3 squared minus 27. All right, take this. Two-thirds here to the fourth minus, now there's two pieces here. I don't want to mess up with that, forgetting to distribute the minus sign. So I'm going to put minus brackets for this whole thing. Oh, wait, I'm just going to sub 0 in. So I don't have to worry about it, it's just 0. But it is something to think about. But not now. Now we just got to clean this up. Hopefully it equals 16 over 12, or we did something bad. Let's just ask for the machine to simplify it. By the way, 16 over 12 is 4/3. So if I go simplify, 4/3, yep. So both ways are the same. Both ways are equal. And they were equally, well, actually, I'm about to say they were equally easier, but I think the top way was a little bit easier. But I couldn't have foreseen that. And the main thing, the main takeaway from here is drawing the picture. Whichever way you choose, the inside ones are curves and the outside ones are numbers. So it goes curve to curve, number to number. So if I'm looking at this one here, I'm doing y's, so y's are vertical, so I'm starting on the smallest curve, written as y equals, and that going to the tallest curve, written as y equals. Why do I need to write them as y equals? So that if there's any x's in them, they get subbed in after I integrate. Let's do another example. And this example, I've been saying pause the video, and I know you didn't. It would really be good to just pause now and just redo this question. Pick one of the ways, draw the picture. It's the drawing the picture and getting the endpoints that's the main meat of this whole non-rectangular region idea. That's the thing you want to get. The actual integrating, I'm integrating y and y squared. The integration is super straightforward. Once we get it set up, the rest of the question is easy to do once it's set up correctly. So much so that I've seen on tests and midterms and stuff, sometimes professors just ask for set up and do not evaluate. They don't even care for you to solve it because that's the easy part. They just want to see you set up the integral correctly. All right, let's do another question. Oh, and this is like a weird question then. Find the average positive value of the function in the first octant. Oh, okay. So I'm going to have to go back to single variable calculus for a second and try and remember my average value function. The average value function, if we remember right, was an application of the integration. So if I wanted to know the average y value, excuse me, that's all. And some reason caps lock is on. Anyway, that took a while, but there's the average value. Read it as the area under the curve divided by the length of that curve. And it kind of makes sense, right? Because if this was an area being like meters squared, I'm looking for the average height of the curve. So meters squared divided by meters would give me meters. The average, would be the proper, the units make sense. I want the volume equivalent. So if I do a double integral, then it would be meters over an area. This would be meters cubed. And I want the average height. So I want to divide it by, if this was meters cubed, so let's write our formula in here. Let's extend this for a volume. So I'm going to have a double integral, and I mean, I don't know what the shape is, so I'm just going to have to say over a region. And I don't know if it's dx dy or dy dx first, so I'm going to put a dA. So this would be the volume, and that would be in cubic meters. I want to divide it out not by the length of but by the area. So this will be cubic meters divided by meters squared. That would give me the average, like the average height. Just like this gives me the average height, or average F value. This gives me the average, F value. So this is the idea that we want to talk about here. And double integral, curve, got to draw the shape. If I'm looking at this shape, and it's the positive value in the first octant, so, all right, let's draw our shape here. I'm only in the first octant, and this looks like where the positive value, so if I were to draw the z equals 0, which would be like the dividing point between when z is positive and when z is negative, that would be x squared plus y squared equals 1, a circle of radius 1, but I'm only in the first octant. So this is the region that we're talking about. We recognize this, if we were to move those over, it's a paraboloid. So we're getting, once we get the volume of this, because I need that for this piece, we're getting the, I guess, the quarter volume of the paraboloid. Anyway, so here's our shape. So if I want the area of this, actually the area, we could do, I could integrate this shape using calculus, but we know that it's a quarter of a circle whose radius is 1. So the area of a circle is, the area is going to be a quarter of that pi radius squared. So the area is just pi over 4. So that area part's just pi over 4. We already know what that is. I just need to get this volume. So to get this volume piece, here's where we're going to pick a double integral. The function, I got the function. And now do I want to go dx dy or dy dx? It probably doesn't matter because the shape is all symmetric. So let's just do dy dx. I'm picking that arbitrarily. Let's see. It's going to go curve to curve. Now if I'm doing y's, doing y first, so I'm in the vertical. So at here the y's are going to start on the curve, y equals 0, and end on this curve. Start on the curve, y equals 0, and end on that curve. Curve. So I need to write this. That's the curve x squared plus y squared is equal to 1. I need to write it as over here I'm going to write y equals 0. I'm starting on, so I need this to be y equals. If that's a dy, these have to be y's. So I'm solving for y. Y is equal to plus or minus the square root of 1 minus x squared, but I'm picking the plus because it's the positive end of it. Now x's, lowest x in the shape, 0, highest x in the shape. number, number. Inside ones are curves, outside ones are numbers. So when I evaluate this integral, I'm going to get the volume. I'm going to get the volume of this surface with this region, this R footprint, and this 1 minus x squared minus y squared as the roof. So in our case, when I go 1 over pi over 4, that's like, let's just invert and multiply. And we just need this here. And we decided to go dx dy first. Y was starting on the curve y equals 0 and ending on the curve square root of 1 minus x squared. And then x was going from 0 to 1. Okay. All I have to do, I say cavalierly, is do this integration. So the setting up the double integral part is over. The rest is just mechanical. That said, it's not necessarily going to be super straightforward, but let's do it. I'm integrating with respect to y. I'm going to throw square brackets around that because we do that. So that's going to be equal to if I integrate with respect to y, that's going to be a y, that's a x squared y, and this will be a y cubed over 3. There's my integration. I want to integrate now from 0 to y equals square root of. Okay, so now I got to go sub in the top minus sub in the bottom for y's. And luckily, and then minus 0. So I sub that in for y. I sub that in for y. I sub this in for y. Minus 0. Now all I got to do is integrate this, which may or may not be easy. If we simplify this, let's simplify that. Now all I have to do is do this integration. Should I do a trig substitution? A u substitution? What about if I just do this? Oh yeah, that's so much easier. Okay, I totally cheated. I just made the machine do it. The pi's gone, so the machine must have used trig substitution to do it. But anyway, the average value is a half over this shape. Now, this looks super cheap, right? You're sitting there watching the video and you're thinking, I feel cheated. I wanted to watch him do like another 10 minutes of integration using trig substitution. Sorry. You can go back and watch a trig substitution video if you need your trig sub fix. Or just accept that that's the way we did it, and we can move on. Because remember, the main point is the setup for this. Let's do another example then. Oh, and the setup for this, and we've introduced the idea of average value with a double integral. So it's like an application of double integration. All right, another example. And this seems like a weird example. Find the area, the regions between the curves. If we were to draw this, if we were to plot this, and then I don't want to put it there, I'll put it over here. Let's plot this one first. I want to plot both of them on the same window. So I'm looking at this region here, and they intersected 0 and 2. So let's zoom in our view here. I don't need to see anything. I don't need to see anything like way back here. So they intersected 0. Let's just make this like 2.2 or something. Okay, and it looks like maximum heights here around 1, which would be, what, 3. So I don't need to see anything in the y's past -2 and maybe 3. So I'm there. That's nice. So I'm looking for this area. Now you're looking at this, you're going, well, why is this a double integral problem? Wouldn't I do area between two curves? That's a first-year calculus problem. We'd go the top curve, which must be the upside down parabola, the top curve minus the bottom curve, and I'll just integrate from 1 to 2. So if this was single variable calculus class, you'd go top curve, excuse me, minus the bottom curve, dx, and you'd start at 0 and you'd end at 2, and you'd get an answer, right? And the integration is going to be pretty straightforward. So this is an already solved problem. How do we relate this to double integrals? Well, if we wanted to make this 3D, and I was thinking about this as the footprint, what function would I make as a roof so that the volume of it in cubic meters equaled the area of it in square meters, the numeric value? Well, I just make it 1 meter high over the whole surface. And then if I got 8 cubic meters, it would have a footprint of 8 square meters because it was a height of 1. So I'm going to make the height 1 and then integrate over the area that way. That's going to give me the volume, but I'm going to interpret it as the area. So let's choose, I'm going to choose dx dy because of dy dx from the way it's written. And look at my picture. It goes curve. So curve, all the y's always start on this bottom curve, which is the curve y equals x times x minus 2. And they end on the curve 3x 2 minus. They end on the upside down parabola. There's my y's. And now x's. Lowest x in the shape 0, highest x in the shape 2. So here, this is now written as a multivariable. But of course, when I do my first integration, I'm integrating 1 with respect to y. I get y. So let's just do this then. When I integrate the 1, I get y. And then I'm going to go sub in the top minus sub in the bottom. And when I go sum in the top minus sum in the bottom, what am I going to get? I'm getting this. And then I evaluate that answer, but it's going to be in meters cubed because I originally started out with a volume. But the numeric answer is the same. So we're not even going to finish this because this is, well, I'll just ask the machine to do it because this integration is pretty straightforward. And we could have done that in Calc 1. The only point I'm making is that is the connection between volume and area when the roof function is just a constant z equals 1. That's all I'm saying here. Let's do another example. Here's one now. Okay, it's a double integral, dx dy. I got to integrate this with respect to x. Now, that looks like trig sub. Oh, but let's just look at the footprint for a second. If I look at this footprint, this is the curve x equals y, which is this line here. If I write it x equals y or y equals x, the same thing. And this is the curve x equals 1. So all the way through this shape, we're starting on, for x's, we're always starting on this line and ending on this line, curve to curve, curve to curve. And then for the y's, lowest y in the shape is that 0, highest y in that shape is that 1. So the region, the R, the region we're talking about here is that triangle. I'm reading the region from the endpoints. It has nothing, so what I wrote down here has nothing to do with this square root of x squared plus 3. The footprint is just given by the endpoints and the order of dx dy. So I could, and I will, switch the order of integration. So I'm trying this out. I'm going to do dy first and then dx. So in my shape, if I'm doing y first, my y's are starting on the curve y equals 0 and ending on the curve y equals x. So I'm going from y equals 0 to y equals x. And now my x's, lowest x in the shape is 0, highest x in the shape is 1. So this answer and this answer are the same numerically. But I like this answer a lot more as far as doing it because I can do that integration. I can integrate this with respect to y. There's no y's in it. So with this, at least the first integration is easier rather than doing a trig sub. Let's see how far we can get. Oh, and before we do jump into that, there are sometimes questions in homework, quizzes, midterms, final exams, whatever, when we learn multivariable, that that's the whole question. They give you an integral and they just say switch the order of integration. So that's the answer. They don't even want you to integrate it. Sometimes they don't even give you what the function is. It's just written as f. And all they want you to do is read the region, draw the region, switch the order of integration. Again, don't be one of those people that try and skip the drawing of the picture thing and try to imagine it. You're just asking for yourself to screw it up. Draw the picture. Read from the picture. Anyway, let's see what we got here as far as we can do this. The picture proves me, or indicates to me, shows me, that this is the same thing, but I'm going to go y first and then x. 0 to 1 for the x's, but 0 to x for the y's. All right, let's do our integration. That's just going to be y times that. And I still have to go from 0 to x. So I integrated that function. Now sub in the top minus sub in the bottom. When I sub in the x for y, minus when I sub in the 0, it's like minus 0, so I won't write it. Now, I still have that square root sign, but my integration is a lot easier now. I could use a u substitution, or I think we can evaluate this, just by inspection. If I did a u substitution, u would equal to u squared plus 3, and that x on the outside would be there to cancel it off. Here I had to do trig sub to do the x first, but now regular u substitution is going to do it. So at this point, I know we can do it with a u substitution or just by inspection. So let's let the machine do it. And I get an answer. So the point of this was why I might want to switch the order of integration. Now I might want to switch the order of integration because the question is just switch the order of integration. Or I might because it gives me an easier integration to do. Here's another example. Oh, and they've written this one as dA. So it could be dx dy or it could be dy dx. Maybe we'll draw the picture and see which one it is. Although upon closer inspection, I don't have choices. If this goes from 0 to x, this must be y equals 0 and y equals x. So it's not like I have a choice. It has to be y first. That's the point of this question. So when we do our integration, I'm integrating this expression with respect to y first. So it's a constant with respect to y. And now it's going to be for y, subbing in the top minus subbing in the bottom. So when I sub in x, that's going to be x squared. And when I sub in 0, it's just going to be 0. So it's a matter of do this integration. And that's regular single variable calculus integration. I'm going to do that by integration by parts twice, or there's a reduction formula. Or that's how I would do it, pencil and paper. I'm just going to ask the machine to do it. And then you can check it, pencil and paper. Point of this, thought I had a choice, didn't have a choice. Now it's all practice. And you gotta draw the picture.